Hello everyone, today we're gonna talk about our paper Continuous Geodesic Convolution for learning on 3D shapes. Many state-of-art methods are using shape descriptor as input to their network. For example, FMNet, PPF, and MeshCNN are pre-computing descriptors on the mesh first, then design their network for downstream tasks. Inspired by the trend of 2D image, we want to do better with raw mesh. Learning from raw mesh on 3D shape is still a challenge. Here we introduce the continuous graph convolution layer, which is trying to mimic the convolution on 2D images. For the central point x, we gather its neighboring points ys within certain geodesic radius and use furthest point sampling to sample fixed number of vertices by having its neighbor carrying its geodesic features, position, normal, and geodesic distance. To regress a weight for doing convolution, different points at different locations will be treated differently. The upper figure shows a more detailed pipeline of our continuous geodesic convolution, and for each vertex in the recept field will take its geodesic distance, position, and normal relative to the central vertex to regress its own weight for convolution operation, such that every continuous point on the manifold has its unique convolution weight. And that's the reason why we call it continuous geodesic convolution. By having a local reference frame attached to the central vertex, the feature we finally get from the convolution layer is rotation invariant. By applying the weight to the input feature, we could get a new feature for the central vertex. The figure shows the architecture of our network. By stacking the convolution layers, we could get a learned deep feature on the input shape. Depending on the downstream task, we could either gather the feature from a second shape to find correspondence using FMNet, or we could append fully connected network to do the segmentation task. We will now see more results. Here is a result on the human body segmentation dataset. We compare with some state-of-the-art 3D neural networks such as DGCNN, MDGCNN, PointNet++, and our accuracy outperforms other methods. Also, because our network is a rotation invariant, so our result is not affected by whether having rotation-based data augmentation during training or test. For the shape correspondence task, we plot the Kim curve comparing with other methods that are using shape descriptors. You could see our curve, the orange one, is above the FMNet one with black color, which is using short as input. The lower figure showed how the texture is transformed from the source shape on the left to the target shape on the right by using the correspondence found by our network. And here are some more results. We have done an ablation study to justify the design of our network. All of the design ingredients play a role in getting the best performance of our network, including the continuous convolution, the geodesic distance, the normal, the local reference frame, the feature from previous layer, and the relative location. Thank you. For more details, please see the paper and come talk to us. The paper ID is 129.